Okay, so all I was saying earlier is radon falls apart and you don't want it in your house. You can test for it. It's nothing to be particularly scared of, but be aware. It can be an issue in some parts of the country. Other parts of the country, it's not really an issue. So it may surprise you whether it is an issue or not around here. In any case, the nuclear force, as they say it, I'm saying it's the strong force because it is trillions of times stronger than gravity. You have your four forces. You have your gravity, you have your electromagnetic force, which is what the electrons in atoms do. That's what makes your hands warm when you rub them together from friction. It's what makes any sort of electronic machine work. Moving electrons around is a wonderful thing. We've only really begun to harness it the last couple hundred years with being able to send electricity through wires or use moving magnets to create electricity. Thank you, Michael Faraday. But in any case, something that's much stronger than both of those forces put together is what goes on not in the electron cloud, that's electric, and not when you get a whole bunch of stuff together like the whole Earth and people, but for gravity. But just inside the nucleus, which is if the atom is the size of the football field, then the nucleus is the size of a quarter. So right there is where you've got the strong force. You don't have it anywhere else in the atom. It's just in the nucleus, but it keeps the things together that normally would love to fly apart. They don't really want to be near each other if you just look at electromagnetic. You got all these positive things in there and a whole bunch of positive things in a nucleus. They want to fly apart if you just look at electric things. And this is why it's so hard to do nuclear fusion, to force uh, the nuclei of like a hydrogen and a lithium atom together to make a couple of helium atoms. Not easy, not easy at all to overcome that electric force. But once you do, once you get them close enough, then they will get together and the strong force will bind them together. The other force in the universe, there are only four forces. The other force is called the weak force, and that's what causes really heavy nuclei to fall apart. That's why past lead, maybe bismuth, but past lead, there's no nucleus that is completely stable. They all fall apart past that. So you've got really about 80 elements that really truly exist for all time. So as opposed to 118 that they put on the periodic table. So, and if you know about half of those 80, then you know a good amount. Very, very useful. So, but anyway, back to this. They are going to hold the nucleus together, but sometimes they don't if things aren't in good balance. So, for instance, if I just have the same number of neutrons as protons, so you see here on the independent axis, you've got protons, that gives the identity to the atom, and then you've got the number of neutrons, and that is less important. An atom of tin is an atom of tin. Doesn't matter how many neutrons it has. But the more protons you have, the more neutrons you need. More neutrons you need. So yeah, you can have 1-to-1 ratio on the light stuff up to calcium, but then you've got to have more than double. You got to have like 1.5 times as much. So if you look at lead, then you'll see there are 82 protons, but more than 200 total things in the nucleus. So like 207, if I remember correctly. Well, if you just doubled 82, that's 164. So there's an extra 40 neutrons in there besides just making it equal. So it's a big deal. It's a big deal. 120 versus 80, that's 1.5. So they'll just fall apart otherwise. So this band of stability, this scatter plot here, these are all the nucleons that are stable. And you'll see that it's kind of, it's dots. It's not a straight line. It's not a straight curve. It's a region. It's a region, and that is something to keep in mind. That until you actually know this stuff, you won't see this band of stability. So 100 years ago, they were just getting information about this, and it was completely brand new. They didn't know about this before. So like Dalton, when he said that all atoms for an element are exactly the same and they last forever, you can't destroy them, he was close, but it wasn't the whole truth. So, all right. I said that already. So, different reasons things may fall apart. Maybe you have too many neutrons. If you have too many neutrons, so it's all the stuff that's above this. Actually, let me move this. Right, there we go. All right. So maybe it's up here. It's to the left of this line. It's above this purple line. You have too many neutrons for the number of protons you have. So what happens then? Well, you're going to have, if you have too many, you're going to have a beta particle shoot out. Again, look at the graph. If you have too many, then what's going to happen is a neutron will fall apart and it'll drop down into the band of stability. It'll drop down to the band of stability, and then it'll be stable. Now what happens is neutrons fall apart all the time and shoot out these beta particles all the time, even in stable atoms. But in a stable atom, there will be enough protons there that one proton will grab onto that electron, that beta particle, and form a new neutron. So you never notice the difference. But they're always falling apart. It's just that when you have too many neutrons, when they fall apart, there's nobody there. It's like playing baseball and you have nobody in the outfield. As soon as you hit even like a single past the infield, you're going to get a lot of bases. And so that's what happens here, is there's just not enough protons to capture the electron, so the beta particle escapes the whole atom, shoots out, gives you a burn on your finger, and the atom goes down to the band of stability. And of course, when that happens, it not only goes down to the band of stability, it goes one to the right as well. So either way, going down, going to the right, or both, which is really what happens, then it gets to this band of stability really quickly. Too many neutrons, you go from left to right on the graph. And that is beta emission. And you can look at the math there. 1 and -1 make 0. 1 and 0 make 1. It all works out. And some famous examples here. The second one, carbon-14. Carbon-14 is made by radiation from the sun, hitting regular old carbon dioxide floating around in the air. It hits the carbon, and it gives it a couple extra neutrons. These are things that are being shot out from the sun. And I won't get into that right now. But in any case, it makes carbon-14 instead of the normal carbon-12. And that's too many neutrons. And so back up to the graph, too many neutrons, and so the number of neutrons goes down by 1 by becoming a proton. So it goes over to the right and down both. And then you've got normal nitrogen. And then it's stable. Normal nitrogen stays that way, and it doesn't keep on having a nuclear reaction. It's all done. But this electron shoots out. But what's interesting is carbon-14 is always being made by the sun in the atmosphere, and it's always being ingested, breathed in, or breathed in by plants or whatever, at a particularly constant rate. And so then when the thing is dead and buried, and you can't add any more carbon-14 to it, the carbon-14 goes away. And so we can tell how many thousands of years old a dead plant is if it's been buried, and nothing's eaten it. We can tell because the ratio between nitrogen and carbon in it will tell us how old it is. It's an amazing thing. The ratio does, because it always falls apart at a very particular rate. I don't know when one particular atom is going to fall apart, but if I've got 1 billion atoms, I know that 500 million will fall apart pretty quickly. All right. What about the opposite? If I have too few neutrons, okay, so back up to the graph, I'm over here to the right. So I could be to the left, or I could be to the right. And if I'm to the right, I can't all of a sudden just like jump up and make a neutron, can I? I actually can. I actually can. If one of two ways, either I capture an electron, maybe a beta particle from some other atom that just shot it out. I capture an electron, and then all of a sudden, the proton that's in the nucleus and this electron fuse and they become a neutron. So the total number of things in the nucleus didn't change, but the number of protons went down by 1 and the number of neutrons went up by 1. And so instead of having nickel, I've got cobalt. It weighs the exact same amount, but it's going to behave differently because it's a different element now. And again, argon chlorine dating, you can measure that as well. Not as common as argon potassium, but and again, these things do happen. The other way to do it is to just shoot out the opposite of an electron. It's called a positron. So if you think of electrons being negative, negatron, then you have positron, positive, shooting out, posit, right? And this is actually a thing. Have you heard of positrons before? Positrons. Well, now you have. Positron is positive electron. It is exactly the same thing as an electron, but instead of being negative, it's positive. It's the antimatter of electrons, so as soon as it gets shot out, it will draw an electron to itself, and it will annihilate. It will release just some energy there. So you can't ever actually like see positrons because they instantly get annihilated with electrons. But one of the great problems in the universe is, at least as far as scientists is concerned, why do we have regular matter? When the Big Bang happened, we should have had an equal amount of matter and antimatter. We should have had an equal number of protons and electrons, but we didn't. Why not? They should have just wiped each other out. The universe should have been made and annihilated itself, but it didn't. Anybody out there have an idea? You get this right, you get the Nobel Prize. They haven't figured it out yet. Anybody want a Nobel Prize? Would you like a Nobel Prize? Explain why there's stuff in the universe. It shouldn't have happened. Everything should have been balanced out and then annihilated itself. Anyway, you can look into it some more. It's a problem. It's a problem. Why is there stuff? All right. Maybe that's too much philosophy, but anyway, that's where science comes from, natural philosophy. So anyway, everything that is bigger than 83, this is the third kind, is just too big, just too big. And so they don't just shoot out an electron here or a positron there or absorb an electron. They shoot out big old chunks of themselves, alpha particles. So I know if something is really big and it's radioactive, it's not going to just shoot out a little tiny electron. It's going to shoot out alpha particles. Okay, and that's what happens here. Radium becomes radon. And radon does the same thing and becomes polonium, which instantly becomes lead. And then it's done. But radium is, maybe you've heard of the radium girls. Radium is, it glows. It glows, it radiates. And they would used to mix it in with paint to have a watch that would glow in the dark about 100 years ago. And then they would take the paint and they would paint it onto watch faces, and it would glow all the time. You didn't have to turn it on or turn it off. It would just always glow. But the thing about paintbrush is every so often you have to, lick it to make it a nice point. And they employed a lot of women to do this painting. Well, what they didn't realize is all this radiation was giving these girls cancer. Eventually they realized it, but it was too late for a lot of them by then. And where do we get radium from? We get it from thorium. Where do we get thorium from? We get it from uranium. So there's a lot of uranium on Earth for some weird reason. It's an excessive amount compared to what we found in anywhere else in the universe. But yay, keeps the crust warm because we're too far from the sun to have liquid water if we didn't have the uranium keeping the Earth warm by breaking apart. But eventually, you know, going through there, the uranium becomes thorium, becomes radium, becomes radon, becomes polonium, becomes lead. And there's a bit more to the story than that. But it's just so heavy they just shoot out helium atom after helium atom. All right. We haven't really done much chemical reactions, so you may or may not know this, but conservation of mass is really important. But not nuclear reactions, because some of the mass literally goes away and becomes energy. And this was Einstein's famous equation that if you take the amount of mass you lose in a nuclear reaction and multiply it times the speed of light, which is a huge number, and then multiply it times the speed of light again, you get the amount of energy that was just released in that nuclear reaction. It's an insanely huge amount. And then when Einstein realized what could happen if you got a lot of uranium together and made a chain reaction to release a lot of energy at once, you know, Einstein from Switzerland, Germany, that area, he was afraid of a certain German dictator whose name you all know. And he said, you know, if this guy gets this before we do, he's going to kill everybody. Everybody who doesn't look like him. And so he told the president of the US, Roosevelt, hey, we better make an atomic bomb before Hitler does. And America did. Hitler was kind of close. He knew what he was trying to do. It was just hard to get the uranium. Yay, history. And ever since World War II, we haven't had a nuclear war. Yay! Because we've been too afraid about what happened if one ever got started. You know, some countries, they still want to do that. So to review, if the atomic number, that's the number of protons, decreases by 1, but you don't change the mass number, then what kind of radiation is emitted? Well, if I shot out a proton, then the mass number would be changed because a proton's really heavy. Same thing with an alpha particle. That's 2 protons and 2 neutrons. That's even worse than a proton. But did I shoot out a beta particle or a positron if I lowered the atomic number? Which one was it? I have 1 fewer positive things. Something positive went away. And remember, it's not going to be a proton or an alpha particle, because if those left, then the mass would change. But this is unchanged. Move this up a bit. So you say a beta particle. Someone else says C as well. All right. Well, if a beta particle went out, a beta particle, remember, is an electron. And its atomic number is actually -1. So if you subtract a -1, then your atomic number would actually increase. If you subtract a negative thing, your atomic number increases. So it's actually a positron. A positron left. Okay? I know it's weird. To subtract a negative thing makes something else grow. But think about this way. You've been in classes where there's like this one really disruptive student, right? And as soon as they get sent to the office, all of a sudden things calm down. All right, think about that. Subtracting negative, what's left behind is more positive. So, and that's where we're going to stop because half-life is a whole nother part to this, so we're going to stop there. Please use the rest of the time, which is about 23 minutes or so, to work on other things that you need to work on. And please do ask any questions. Please don't leave the Zoom call, though. I still need to take attendance. So I'm going to turn on the lights in here, so be prepared for the lights to come back on. Bye. I got a big minute. So do 5. That's good. Oh, and I'll go ahead and stop the recording now, too.